Hello everyone, myself Mrs. Archana Bhar in Electronics and Telecommunication Department. In this video, we are going to continue with the third unit of Basic Electronics, that is bipolar junction transistor. Here first we will see fixed bias circuit. The simplest biasing circuit used to bias a BJT is called as fixed bias circuit. This is the circuit diagram for fixed bias circuit. In this circuit, only one power supply VCC has been used to supply power to collector as well as base. In this diagram, you can see VCC is a supply which is used to supply power to this collector terminal as well as base terminal of BJT. RB is a single base biasing resistor, hence this circuit is also called as single base resistor biasing. Analysis of fixed bias circuit. Step 1. Expression for the base current IB. Apply the Kirchhoff voltage law to the base circuit. So we'll get the equation as VCC minus IBRB minus VBE is equal to 0. Rearranging the equation, we'll get IB is equal to VCC minus VBE divided by RB. Step 2. To calculate the value of IC. So expressions for IC. The fixed bias circuit is designed to operate in the active region, hence IC is equal to beta IB. Step number 3 is expression for VCE. VCC minus ICRC minus VCE is equal to 0. So VCE is equal to VCC minus ICRC. Now next is a base bias with emitter feedback. This circuit is as shown in figure. The base bias circuit emitter feedback is also called as modified fixed bias circuit. The resistance RE has been added from the emitter to ground terminal in the fixed bias circuit. The emitter resistor improves the bias point stability. Now this is the analysis of base bias with emitter feedback. Here first we'll apply the KVL to the base circuit. So we'll get the equation as VCC minus VCC is equal to IBRB plus VBE plus IERE is equal to so IE is equal to IC plus IB and IC is equal to beta DC into IB. Then substituting the value of IC and IE in equation number 5.4.5. So we will get this equation. So rearranging the equation, we will get the value of IB is equal to VCC minus VB divided by RB plus into bracket 1 plus beta into RE. Now expression for the base current at Q point, that is IBQ. Here we will apply the KVL to the collector side, that is output side. So we'll get the equation VCC is equal to IC RC plus VCE plus IE R. So bias stabilization of this type of biasing technique is if temperature increases, then IC and IE will also increases. So emitter voltage VE is equal to IERE increases, but VB is constant, so VBE decreases. So IB will decreases, so IC will reduce because IC is equal to beta IB. Thus increased IC will be reduced back to its desired Q point value and stabilization is achieved. Now voltage divider bias. So this is the diagram for the voltage divider biasing technique. The resistor R1 and R2 form a potential divider to apply a fixed voltage VB to the base. A resistance RE has been connected in the emitter circuit. Now analysis of voltage divider bias. Base circuit. Consider the base circuit. Here we assume that the collector and emitter terminals are open circuited. The base voltage VB is nothing but the voltage across resistor R2. VB is equal to VR2 is equal to R2 divided by R1 plus R2 into VCC. This is because current through R1 and R2 is approximately same and is equal to I. Then collector circuit, the voltage across emitter resistance Re can be obtained as follows. V is equal to IE is equal to VB minus VBE. Therefore, IE is equal to VB minus VBE divided by Re. Applying the KVL to the collector circuit will get VCC is equal to ICRC plus VCE plus REIE. Therefore, VCE is equal to VCC minus ICRC minus IERE. Then procedure for exact analysis for voltage divider bias. Thevenin's equivalent circuit. So this is the figure diagram, circuit diagram, which shows the Thevenin's equivalent circuit for voltage divider bias. The Thevenin's equivalent of the circuit of the voltage divider bias is shown in figure. The resistance R1 and R2 are replaced by RB and VTH, where VTH is the Thevenin's voltage and RB is the Thevenin's equivalent resistor, which is equal to the parallel combination of R1 and R2. So RTH is equal to R1 parallel to R2. So we'll write 1 divided by RTH is equal to 1 divided by R1 plus 1 divided by R2. And VTH is equal to VCC into bracket R2 divided by R1 plus R2. Then step 2, obtain the expression for IP. For that, we'll apply KVL to the base loop circuit. So we'll get the equation as VTH minus IBRB minus VBE minus IR is equal to 0. So rearranging the equation, we'll get the value of IP, that is base current, is equal to VTH minus VBE divided by RB plus 1 plus beta into RE. Then next step is to obtain the expression for collector current and obtain the expression for VCE. For that, we'll apply the KVL to the collector loop. Then next point is thermal runaway. The collector region of the transistor dissipates heat. As we increase the amount of power dissipated in transistor, its junction temperature increases. The maximum power that a transistor can dissipate without getting damaged depends on the maximum temperature that a collector base junction can withstand. The rise in the collector base junction takes place due to two reasons. First is due to increase in the ambient, that is surrounding temperature, and due to the internal heating. Out of them, the internal heating process is explained below. First point is, as an increase in the collector current IC increases the power dissipated in the collector base junction of the transistor. This will increase the temperature of CB junction. As the transistor has a negative temperature coefficient of resistivity, increased junction temperature reduces its internal resistance. The reduced resistance will increase the collector current further. This becomes a cumulative process which will finally damage the transistor due to excessive internal heating. This process is known as thermal runaway. Now here shows how the thermal runaway takes place. When collector current increases, the power dissipation increases. Then this will increase in the temperature of collector base junction, and resultant resistance of the device decreases, and again resistance decreases, then IC collector current will increases. So how to avoid the thermal runaway? Never exceed the collector current beyond a certain maximum specified by the manufacturer. Maximum value specified by the manufacturer. Never exceed the internal power dissipation above the maximum permissible value. Use heat sink to radiate the heat into atmosphere. Thank you.